Okay, you guys, this is example problems. Example problems from chapter 7. All right, 7.1. 7.1 says height of a baseball from energy considerations. All right, and it states you throw a 0.145 kg baseball straight up, giving it an initial velocity of 20 meters per second. So VI mass equals and VI equals 20 meters per second. Find out how high it goes, ignoring air resistance. We're going to do this by conservation of energy. mgh equals 1/2 mv squared. Well, I don't need the m, so I'm going to say I want to solve for h. H equals v squared over 2g. So h is going to equal to 20 meters per second. Quantity squared divided by 2 times 9.8 meters per second squared. And that's going to equal to 20.4 meters. 20.4 meters. Continuing on. 7.2 is work and energy in throwing a baseball. And it says, in example 7.1, suppose your hand moves upward by 0.005 meters. So delta hand equals 0.5 meters. While you were throwing the ball leaves your hand with an initial velocity of 20 meters per second. V initial equals 20.0 meters per second. And mass was 0.145 kgs. 0.145 kgs. Find the magnitude of the force your hand exerts on the ball. Find the speed of the ball at 15 meters above the point where it leaves your hand. Ignore air resistance. Okay, so the work, so we've got K initial plus U initial plus the work by other forces, outside forces, equals K final plus U final. We know the initial, that's 0 and that's 0. So this guy is, we have to solve for that. So work equals 1/2 0.145 kg times 20 meters per second quantity squared plus 0.145 kg times 9.8 meters per second squared times 0.5 meters. Oh, come on now. There we go. All right, so my work, if I do all the math, the work is going to be equal to 29.7 joules, 29.7 joules. But my work is going to be equal to the force over the distance. So 29.7 joules equals my force. And the distance that my hand worked was 0.50 meters. So force is going to be equal to 29.7 joules over 0.50 meters. And that's going to be equal to 59 newtons, 59 newtons. That's my force. All right, I'm going to pause, clean my board, and continue. Okay, now I want to know how fast it's going when it is, 15 meters above the point where it left my hand. So I'm going to use my energy considerations. So my K plus U K1 U1 equals K2 U plus U2. So I know this guy from here is 29.7 joules. So 29.7 joules equals, I'm solving for this. I'm going to go MGH plus K2. So I'm going to take 29.7 joules minus 0.145 kgs. 1 second. Oh, okay, so where was I? I was taking my initial total energy minusing my potential energy that I gained, and I'm going to get my kinetic energy and solve for my new velocity. So that's times 9.8 meters per second squared, times my height, delta H is 15 meters. And I'm going to get for that value 7.7 joules. If you do the math, you get 7.7 joules. And now you're going to convert that into a kinetic energy. So 7.7 joules equals 1/2 mv squared. So 2 times 7.7 joules divided by m, which is 0.145 kg. Under the radical is going to give me v. So now coming over here, and v is going to give me plus or minus 10 meters per second. Okay, so that's just going to be, I'm assuming it's going up. Yeah, oh, it doesn't matter. That's 10 meters where I left it. If it left here, it doesn't matter if it's going up or down. If it's going up, it's 10 meters. If it's coming down, it's minus 10 meters per second. Meters per second. There you go. And that's 7.2. All right, 7.3 is a thought problem, and it is energy in projectile motion. And it says a batter hits two identical baseballs with the same initial speed and from the same initial height, but at different initial angles. Prove that both balls have the same speed at any height h if air resistance can be ignored. So we can do that by saying they both have the initial E, and that equals delta K, delta E, right? Or delta work or delta energy plus delta U. And if I have this guy is going to be the same, then that's going to be the same, which means their velocity is going to be the same, providing they are the same baseball. And we do know that they're identical baseballs. So there you go. That's 7.3. 7.4 is speed at the bottom of a vertical circle. And it reads your cousin, Morton, same cousin from the last chapter, skateboards from rest down a curved frictionless ramp. If we treat Throcky and his skateboard as a particle, he moves through a quarter circle with radius r equals 3 meters. R equals 3 meters. Throcky and his skateboard have a total mass of 25 kilograms. Well, he's a little guy, huh? Equals 25.0 kg. And find the speed at the bottom of the ramp. Find the normal force that acts on him at the bottom of the curve. All right. So here's the curve. The radius is here. He starts there. So that means his delta y is 3 meters. And this is a conservative force, so it's independent of the path. So if he starts from rest here, he's going to trade that u in for k. So mgh equals 1/2 mv squared. These m's got to go. And I'm going to solve for v equals the square root of 2gh. So v is going to equal the square root of 2 times 9.8 meters per second squared times 3 meters. And interesting that it's independent of mass, right? And that's going to be equal to 7.67 meters per second. And the second part, I'm supposed to find the, let's see. I am to find the normal force that acts on him at the bottom of the curve. All right, so let me clear and get some space. Okay, so the normal force acting on him at the bottom of the curve. So the sum of the forces in the y are going to be equal to that normal force minus the weight is going to equal to my M.A. radial. So let's see, my normal force is going to equal to the M.A. radial plus the weight. So this is going to be equal to mv squared over r plus mg. So it's going to be equal to m. And what's him in the skateboard? 25 kilograms, 25 kg times 7.67 meters per second quantity squared over, and I believe that was 3 meters plus g. And that whole thing is going to equal to, let's see, 735 newtons, 735 newtons. That's a 5. All right, beautiful. All right, problem 7.5 says a vertical circle with friction. I went on to 7. We're going to do 7.6 and I'll go back to 7.5. All right, 7.6 says an inclined plane with friction. We want to slide a 12 kilogram crate up a 2.5 meter long ramp, inclined at an angle of 30 degrees. By giving it an initial, a worker ignoring friction calculates he can do this by giving it an initial speed of 5 meters per second. So B initial equals 5.0 meters per second. And letting it go. But friction is not negligible. The crate slides only 1.6 meters up the ramp. So delta X equals 1.6 meters. And slides back down. A, find the magnitude of the friction force acting on the crate, assuming that it is constant. B, how fast is the crate moving when it reaches the bottom of the ramp? Okay, we're going to take care of all this. All right, so we slid it up there, it stopped, and that was because of friction. So we have the delta K. We have K1 plus U1 plus work of friction equals K2 plus U2 plus U2. So K1 is 1/2 times 12 kg times, what's our velocity? 5 meters per second quantity squared. This guy's 0, it's at the bottom of the ramp, plus the work of friction equals, and that guy is 0, it stops, plus M is 12 kg, 9.8 meters per second squared. And this would be 1.6 meters. Oh no, wait a minute. That's not 1.6 meters. It is 1.6 sine 30. 1.6 meters sine 30. It is the vertical distance. All right. Now, the book solved it for me, so let's see, what do we get here? That's that. We get that force of friction is going to be equal to 35 newtons. Okay, so let me. Now it wants to know how fast the crate is moving when it gets down to the bottom. So let's see, 35 newtons equals mg times 1.5 sine theta, sine 30, plus k. So 35 newtons divided by 12 kgs times 9.8 meters per second squared times 1.5 sine 30 is going to equal to k. And let's see, k equals 38 joules. 38 joules, and that equals to 1/2 mv squared. So let's see, v is going to be equal to square root of 2 times 38 joules divided by, what was the mass, 12 kg, and that's going to equal to 2.5 meters per second. All right, so 2.5 meters per second. So the next one is a vertical circle with friction. We're going back to 7.5 now. It says, suppose the ramp at example 7.4 is not frictionless, and the Thraki speed at the bottom is only 6 meters per second, not 7.67. So it's 6 meters per second, not 7.67. What work was done on him by the friction force? Okay, so we want to know that we know that K1 plus U1 plus work equals K2 plus U2. All right, so K1 is 0 plus U1 is mgh, which is, let's see, 25 kilograms, kg plus 9.8 meters per second squared plus 3 meters, right? And then this is 0 plus work equals 1/2 times 2.5, 25, 25.0 kg times 6 meters per second, 6.0 meters per second. And we're going to get, let's see, I have to crank this out. The work, okay, we're going to get work is by friction is negative 285 joules. Is that what is the work done by him on the friction force? There we go. So that's the work done by him on the friction force.